Hello and welcome to this video. In this video we will be looking about PIC16F877A using the ADCs, and that is the analog to digital converter. In this example we will be using an LDR as the sensor, and we will be using the ADC to read analog data from the LDR along with the pull-up register connected, and we will then see the software for using the ADC. But now let's first look at the datasheet. So let's waste no more time and jump onto datasheet of PIC16F877A. Click here and open the AD converter here. So you can see here analog to digital converter module. It has eight channel, and for using ADC you have to use the 4 registers: ADC result high register, ADC result low register, AD control register 0 and AD control register 1. Just 4 register. These 2 register, it is very well from the name that these ADCs are used to store the data obtained from the ADC. Since it is a 10-bit ADC, and these are 8-bit shift registers. That's why you have to use 2 registers. We'll be looking it below. But now first let us see the AD con 0 register or the control register 0. ADCS1, ADCS0. These are used to select the conversion bits, the clock conversion, the clock prescaler. You can choose anyone you may like, and only for the 1-1 case this should be obtained from the internal RC oscillator. Better to use the this external oscillator like FOSC by 2, FOSC by 8, and next 3 bits are the CHS2, CHS1 and CHS0. This is nothing but the channel select bits. Since this has 8 channels, so 3 bits, therefore 2 cube 8, so 3 bits, and this is the simple truth table for selection of bits. And go /done bar. It is clear that when AD on equal to 1, AD conversion is in progress. Setting this bit starts the AD conversion, which is automatically cleared by the hardware when the AD conversion is complete, and when 0, AD conversion not in progress. So these informations are very much crystal clear. There is nothing much difficulty in it. And next bit is unimplemented, and last one is the AD on. AD on is just used to set the AD converter on. This is just used as the internal switch inside the inside circuitry present inside the microcontroller. When you set this bit, it will turn on the ADC just as a simple switch like. So this is the AD con 0 register. Now comes the AD con 1 register. The AFDM is the left adjustment or right adjustment. The result for the left adjustment or right adjustment. If 1 right justified, 0 left justified. I am showing you right now what is the meaning of it. So let's jump a little below. Yes, here is the figure. AD result justification. Since it's a 10-bit result and all these registers are 8-bit, that's why the 2 bits needs to be adjusted. So if this for right adjustment, that is ADFM equal to 1, the ADRESL at the left and the ADRESH at the right, the higher 2 bits means the 9th and the 10th bit will be in the ADRESH bits 0 and 1. The rest from bit number 2 to bit number 7 are empty or filled with zeros. And if left justified, then the ADRESH is again at the left, and the ADRE and the ADRESL, the lower byte, the result is left justified, means the 0th and the first byte of the result are at the 7th and the 8th position of the ADRESL, and the rest are filled with zeros. So better is to use the right justified format by setting ADFM equal to 1. We will be showing in the code how to do this. and this is the ADC S2. ADC S2 is from the from this one. This is in continuation with the first register itself. ADC, here we have the ADC S0, ADC S1, and since these have 8, and these can have 8 combinations, so that's why the ADC S2 is in the ADCon 1 register. And now here is the PCFG3 to PCFG0, and these 4 bits for our purpose, since we will be just only using the AD converter, that's why we have set it to 0. All 0000 means all the channels are analog inputs, and the VF is the VDD, the plus 5 volt, and the VF minus is the ground, and CYR is 8:0. For example, in the second configuration, you have this one as the AN3 as the VF plus, so this reduces by 1, that is 7/1, and similarly you can have other combinations too. You can use them as per your application requirement. So now you may try to you may try to look more inside the datasheet, and you may learn something more. And this datasheet are crystal clear, and make it a habit to read the datasheet before using the code. So after observing the datasheet, we will be looking at the code here. Firstly, initially the pragma configuration bits we have to select. We have the high speed oscillations selection, and rest of the you may turn high or low as per your need. Our crystal frequency is 20 megahertz, and now comes the setup ADC function. The setup ADC, just as we looked at the datasheet, we have to set ADFM as right justified into ADCon 1 register, and initially we have to turn on the ADC. Now you have to select which channel you will like to use. So that's why we have to use the parameter inside the function as the index. So based on the channel selection, you can have a switch case like this. So if case 0, channel 0 is selected. If case 1, channel 1 is selected. If case 2, channel 2 is selected. You can very well understand how this code works. This is just bit shifting in C, and you have to fill the ADCon 0 register with these values as per the case statement, means the channel of the ADC you will want to work with. So now I have set up the ADC. Since I will be using channel 0, I will use setup 0. If you want to use more number of sensors, you will have to write as setup ADC 1, setup ADC 2. And now in my PIC board, I have 2 onboard LEDs here. So if the calculate ADC value is greater than 500, the first LED will light up, the second will turn low, and if the value is less than 500, then the first LED will turn low and the second LED will turn on high. And for making both as outputs, I have written as tris B1 equal to 0 and tris D1 equal to 0. By setting 0, you can set the bit as output. Tris B means the tri-state buffer. And now in the calculate ADC function, which I have used here, so in the calculate ADC function, firstly we have to turn on the conversion bit, which initializes the AD conversion, means the go/done bar. So we have to wait. So while go and done, so wait for the AD conversion to complete. After the conversion is complete, it will go and done will turn on to 0, and then we can calculate the value by using bit shifting. Remember, we have the right justified format since ADFM equal to 1, so that's why we have to bit shift 8 and obtain the result and then return it. So we have used the value here. So if greater than 500, we have to switch on the respective LEDs. You may turn it, you may do it vice versa or in the reverse fashion as well. And lastly, a small delay is included. And for this program, actually these 2 header files are not actually required. These 2 header files are actually not required in this case. Only xc.h is enough for this. And if you want to use the delay, if you want to use this underscore delay underscore ms100, you have to define this crystal frequency. If you do not write this, the delay will not work and the code will not compile. So I'll be building this code. For my PIC16F877A, it will take some time, and yes, it is successful. And I am using MPLAB IPE. So it is right now connected, and the power is from the PIC3 itself. So programming is complete, and now we'll be seeing it in action. So uploading is complete, and the sketch is running. So here you can see the LDR, here, and as I bring my finger and close obstruct the light, so you can see this onboard LED has stopped glowing, and the another one turns on, and as I remove, and light falls on it, and so the second one now glows and the first one off, and the vice versa happens when I put my turn. This is my board for my PIC. This is for the PIC kit header. So, and now in very short I will be showing you the circuit for the LDR connection. The LDR, here I have a 6.8 kilo ohm resistance. You can use a 10 kilo ohm resistor as well, and this one is the LDR from this junction to A0, means the analog input 0. This is the circuit I have used. Before ending the video, I would like to talk to you about using float values. So right now, as you have seen that the calculate ADC function is a function which returns an integer, and here I have used integer comparison, means that if value is greater than 500, so turn on the LEDs and so on. And what if I have used voltage values instead of this ADC value? So suppose if I write 2.5 means 500 means actually 2.5 volts. So what if I calculate this ADC into 0.00488? So why this value? This is because 5 divided by 2 to the power 10 gives us the resolution of the 10-bit ADC, which is equal to 4.8 millivolt. So calculate ADC into 4.88 millivolt gives us voltage value. So 500 corresponds to 2.5 volt. So what if I compile this project? See here, data memory 3%, program memory 4%. Right now this sketch occupies, and now after using this float value, see, data memory has been consumed up to 17% and program memory about 20%. So since 8 kilobyte is the flash, so about 20% of 8 kilobyte has been consumed, and you have much less space available. So only for using this float value, you consume too much amount of memory, and you have very much less amount of memory now left. So try to avoid float values. If you can manage with integer, always use integers. Not try to use float values, since this will take up huge lot of memory. So I am return to previous, and then see again, it has 3% and program memory 4%. So always try to use integer variables, and try to avoid float variables unless and until you are in a too much compulsion to use it, like in a sensor based situation where you need to store the actual voltage value. So in that case you might use float, but these are too much expensive. Do not use too much float values in your program. So that's all what I have to say in the video. So thank you for watching the video. If you have any confusion, please do let me know in the comment section. I'll be definitely trying you to help solving them out. So please do like, share and subscribe, and turn on the bell icon for getting further notifications. Thank you.